All right, diving in today, folks, we're going deep, deep down into, well, kind of the basement of math, like the foundation. And the wild thing is, this all connects to how we talk and think every single day. And this journey actually started because you, our awesome listener, asked about this. So we dug up some seriously cool stuff to unpack. We're going to hit those key points without drowning you in, all the nitty-gritty details.
Exactly. It's all about Russell's paradox today. We're going to
Yeah.
trace it back to its origins in set theory and then see why it goes way beyond just a math problem. Like the ripple effects are kind of mind-blowing.
Yeah. And before we go full on deep dive, a quick shout out to the folks who make this whole thing possible, stonefly.com. Stonefly is a solution company, all about data management, been at it for like over 2 decades now, helping businesses make sense of all their data. They're pioneers in like SAN, NAS, S3 object storage, and all this super advanced stuff, AI, advanced security technology, including their object lockdown technology. So big thanks to stonefly.com.
All right, so let's start simple, right? Numbers. Take the number 4. It's all over science, tech. It's like the backbone of how we grasp the world. But have you ever really sat down and pondered what the number 4 actually is? Like, what does it mean?
Okay, so let's break that down. Back in the 1700s, you had Immanuel Kant. He kind of thought math was like a human creation, a way we organize stuff in our heads. So, math truths, for Kant, they were kind of subjective.
hmm
But then, along came guys like Gottlob Frege and Bertrand Russell. They had a totally different idea.
What's super interesting here is their angle. They call it logicism. They believe that math, like at its core, was basically just a part of logic, and they went all in, tried to prove that even basic arithmetic, like adding and stuff, could be built from pure logic and this thing called set theory. Their big goal, was to find this objective foundation for math, right?
Yeah.
Answer that question you just asked, like, what is a number really?
Sets, okay, sets. So when we say set, what picture should we have in mind?
Set theory, well, it's the study of these collections of objects, right? And it was really Georg Cantor, late 19th century, who developed it. And get this, Cantor did some crazy mind-bending work, even proving that there are different sizes of infinity. Like, whoa, right? But to even get there, he had to lay down the basics of what a set even is.
And the kind of set theory we're starting with, it's called naive set theory, right? It's not like super formal, complicated math stuff, but just like how we naturally think about groups of things in normal language.
Exactly. Like just think of
Yeah.
a set as a collection of distinct objects. It could be something concrete, like the keys in your pocket. It could be that set.
Right, right. Or something more abstract, right? We could talk about like everyone listening to this right now all over the place. That's a set too.
Totally. And they don't have to be related, right? Your coffee mug and the planet Jupiter, boom, same set. Two completely different things.
Yeah.
Like you could even have Abraham Lincoln and Harry Potter in a set. One real, one fictional.
It gets even weirder, right? Like what about the set of all things you can't even imagine?
Yeah, that's right. And when we write these sets down, we use these curly brackets, right? So like a set with the number 7 and a rubber duck would look like curly bracket, 7 comma rubber duck, curly bracket. But like for huge sets, like all the stars in the Milky Way, well, writing them all out is impossible. So we use this thing called set builder notation. Looks like this. Curly bracket, X, vertical bar, X is a star in the Milky Way, curly bracket.
And it basically means the set of all x's such that x is a star in the Milky Way.
Right, and the key concept here is contains. If something's inside those curly brackets or it fits the rule in that notation, then the set contains it. And that thing is a member of the set.
Got it. So like Cantor himself, he described a set as, quote, a gathering together into a whole of definite, distinct objects of our perception or of our thought, which are called elements of the set, end quote.
It's like taking a bunch of individual things and thinking about them as one single thing.
And honestly, we use sets all the time without even realizing it. Like when you say that group of friends is always laughing, you're not like zeroing in on each friend, right? You're talking about the whole group, the set of them, or like the population of your city. That's a set, even though everyone's like scattered all over the place.
And speaking of sets, it's within these seemingly simple ideas about sets that Russell he stumbled onto this problem, a real paradox.
Mm-hmm.
And it stems from some of the basic rules of this naive set theory.
Okay, so let's walk through some of these key rules. These are like the ground rules, setting the stage for this unexpected twist.
All right, rule number 1, unrestricted composition. Basically, it says if you can think of a collection of things and clearly define what's in it and what's not, then boom, that collection is a set. If you can describe it, it's a set.
Okay, and rule number 2. A set is totally defined by its members. The order you list them in doesn't matter. And like how you describe them, that doesn't change the set either as long as it's the same stuff inside.
Yeah. Which leads to rule number 3. The order of stuff in a set doesn't matter. So like the set with A and B, it's the same whether you write curly bracket A, B, curly bracket, or, curly bracket B, A, curly bracket. And rule 4, listing the same thing multiple times, it doesn't change the set. So like curly bracket, apple, banana, banana, curly bracket, it's still just the set, curly bracket, apple, banana, curly bracket. Okay, and rule number 5 says that like how you describe those items, it doesn't change the set itself. So the set with the first person to walk on the moon, that's the same as the set with Neil Armstrong. Same person, same element, same set. Right, right. And rule number 6, if you take any 2 sets or more and combine all their members, into a new collection, the new collection is also a set. So like if you have the set of all fruits and the set of all vegetables, their union, that's the fancy word, their union, the set of all fruits and vegetables together, well, that's also a set.
Rule number 7. If you take any subset of a set, like any selection of its members, that subset is also a set. So if you have a set of, I don't know, playing cards, then just the face cards, that's a set too.
Okay, rule number 8. A set can have just one member, and that's called a singleton set. And remember, the singleton set isn't the same thing as the member itself. Like the set containing Mars, the planet, it's not Mars itself. It's like a container with Mars inside.
Right, it's a subtle difference. And rule number 9, a set can be empty, no members at all. That's the empty set or null set written with like empty curly brackets or a circle with a line through it.
Yeah.
There's only one empty set, right?
Yeah.
Because they all contain, well, nothing.
Now, rule number 10, this is where it gets interesting. You can have sets of sets. Since sets are, things we can think about, we can definitely group them into new sets.
Sets within sets.
Yeah, like you could have the set of all singleton sets, right? Or even like, whoa, the set of all sets.
So sets all the way down, huh?
Yeah, and this whole idea of sets of sets, it was like super important for those logicists we talked about, Frege and Russell. They thought like the number 1 was just the set of all singleton sets. The number 2 was the set of all sets with 2 members and so on. It's a very abstract way to think about numbers, for sure.
Yeah, abstract and, as we'll see, a bit tricky. And then the final rule, the one that kind of sets off the fireworks, rule number 11, sets can contain themselves.
Right. Now, that might sound bizarre.
Yeah, a little bit.
But if we can define a set,
right,
and that set happens to fit its own definition, then, well, it can be a member of itself.
So think about like the set of all cats. Does that set contain itself?
No, right. The set of all cats, it's not a cat itself.
Right, it's like a category, not an actual cat.
Exactly. But what about the set of all sets?
Does that contain itself?
Yeah, because the set of all sets is what's a set, so it fits its own description.
Okay, so we have sets that don't contain themselves and sets that do. And here's where Russell comes in with this super insightful and for mathematicians at the time, really disruptive question. He asked, what about the set of all sets that do not contain themselves?
This is the key bit, so think carefully here. We'll call this set R for Russell's set. So R is the set of all sets X, such that X does not contain X. Now, here's the tricky question. Does R contain R?
Whoa, okay, let's play this out. So first, let's say R does contain itself. If it does, then like by definition, its members have got to be sets that don't contain themselves. So if R is a member of itself, it has to be a set that doesn't contain itself. That's like saying up is down, right?
Total contradiction.
Totally. Now, what if R doesn't contain itself?
Okay, so if R is not a member of itself, then it perfectly fits the description of sets that are in R, right? It's a set that doesn't contain itself.
So it should be an R.
Exactly. So by its own definition, R must contain itself. Again, a contradiction.
So no matter how you slice it, it just doesn't make sense. If R is in R, then it's not. If it's not, then it is. This is Russell's paradox. And like, it shook the foundations of math.
And Russell actually shared this paradox in a letter to Frege in 1902. And get this was just as Frege was wrapping up his life's work, trying to like nail down this solid logical basis for math. And this paradox, it showed a flaw, like right at the core of Frege's system. It really hit him hard, apparently.
Yeah, I can imagine. So the first reaction among mathematicians was like, okay, gotta fix this, right? They started looking at those rules of set theory, especially the one about sets containing themselves and that unrestricted composition rule.
This led to, like, more formal, carefully built systems of set theory, like Zermelo-Fraenkel set theory or ZF, basically they put limits on how you could make sets, specifically saying like no sets can't contain themselves and being super careful about what collections could actually be called sets, all to avoid Russell's paradox.
But here's the really mind-blowing part. Russell himself, he argued that these rules of naive set theory, they weren't just like random ideas. He thought they reflected something deeper about how we think and use language. Specifically, this thing called predication.
So in linguistics, predication is just saying something about something else. Every sentence has a subject, what we're talking about, and a predicate, what we're saying about it. Like, the sky is blue, the sky, that's the subject, and is blue is the predicate. And we can say that predicates are true of subjects.
So is blue is true of the sky.
Exactly. And this true of thing, it's really similar to that contains relationship in sets.
Okay, so let's see those connections. Unrestricted composition, that almost any collection can be a set. Well, that seems kind of like how we can make a predicate for almost any characteristic.
Yeah, and just like sets of sets, we can apply predicates to other predicates, like being a long word is true of sesquipedalian. Here, the predicate being a long word is applied to the word sesquipedalian, which itself describes a type of word, a predicate.
Okay, and what about sets containing themselves?
What's like predicates being true of themselves? Like, is a word is true of itself because is a word is, well, a word.
But many predicates aren't true of themselves, right? Like is a cat isn't true of itself. The cat is a predicate, not a cat.
Exactly. So now, think back to Russell's set, the set of all sets that don't contain themselves. What would that be in language?
The predicate is not true of itself.
You got it. So, same question, but in the world of language.
Yeah.
Is not true of itself, true of itself.
Okay, let me think. If it is true of itself, then what it says that it's not true of itself, that has to be true. So if it's true, it's not true.
Another contradiction.
Yeah, and what if is not true of itself is not true of itself?
Well, then it doesn't fit its own description, meaning it is true of itself. So if it's not true, then it is true.
Same kind of contradiction.
This is the profound point. Russell's paradox, it's not just some weird math problem. It points to a deeper issue with language and thought, like the very act of making statements and defining things.
It's like this contradiction is baked into like the fabric of how we think.
Exactly. And now a quick word from our sponsor, Stonefly.com. Stonefly is a solution company that really gets how complex information can be. For over 20 years, Stonefly has been at the forefront of SAN, NAS, S3 object storage, backup and disaster recovery, cloud, AI, and all sorts of cutting-edge security stuff. They've got this advanced AI integration and cyber-resilient architecture, including their patented immutable storage and object lockdown technology, which is that's specifically for protection against ransomware. It all provides a rock-solid foundation for managing critical data. And Stonefly has worked with a huge range of enterprise customers across all kinds of sectors, finance, healthcare, government, you name it. If you want to learn more, head over to stonefly.com. Oh, and they have a special offer this month on their Stonefly DR365V. It's a high-performance appliance, 70 terabytes of storage, fully redundant, and you can expand it up to 4 petabytes. It comes with air-gapped and immutable Veeam, Rubrik, Commvault, site recovery, backup, and DRR, all with object lockdown technology to protect against ransomware, and all that for $7,995. If you're interested or have any questions, you can visit www.stonefly.com. or send them an email at sales@stonefly.com.
Okay, so back to Russell's paradox. We started with this deep dive into what seemed like, an abstract math problem, but it turns out it has these like huge implications that touches on like the limits of our ability to define and categorize things, not just in math, but in like how we use language every day.
It's really wild how this paradox from this, seemingly obscure corner of set theory, it pops up in everyday language. It shows us that even in the most basic ways we describe things, these contradictions can just appear.
Yeah, it's like our brains are kind of wired for these paradoxes in a way.
Maybe. And for you listening, this raises some really important questions, right? Like, how does this paradox change how you think about truth? What about self-referential statements, things that talk about themselves? And maybe it even suggests that any system we create, any formal system to understand the world, it's going to have limitations. It's a puzzle that keeps people thinking, and it reminds us that even in the most rigorous fields like math, there are still these deep mysteries.
Big mysteries in the basement of math. And that brings us to the end of this deep dive. Huge thanks to Stonefly.com, the solution company for data management, for making this possible. Until next time, keep those curious minds going.